Alright, so in this video, what we're going to do is we're going to discuss right triangles more broadly. Now, um, we've done a lot in the previous chapter discussing right triangles associated with points and angles related to the unit circle, but the issue, of course, is that your average triangle that you encounter is not going to necessarily do you the favor of having a hypotenuse of exactly one, right? And so we want to know how to deal with triangles a little bit more broadly in general. So let's take a look at some right triangle. Let's make it bigger. And let's just say that this, just to stick with things maybe we might be a little bit more familiar with, let's say that is 30 degrees. Over here, and then let's say the base of this is 10, and what I want to know now is the rest of my dimensions of this triangle, and let's emphasize the fact that it's a right angle there. Now, what we want to do now is start filling this thing in with things that we can piece together right away. And so the other thing I know is that this angle here is 60 degrees, right? So I know that much at least. Now, I don't know what this hypotenuse is yet. I'm going to call this, let's say maybe, let's give it a different color, and let's call this R for something that we don't know. But I want to step back for a second and think about what this triangle is doing and what it looks like. Now, we've spent so much time looking at and working with triangles of the unit circle that it would be a shame to kind of totally reinvent the wheel when we look at triangles whose hypotenuse is not exactly 1, right? And so is there a way I can look at this triangle and cook up a triangle whose hypotenuse is exactly 1 that sort of behaves the same as this triangle here? So let's come down here and kind of redraw it real quick. Let's so let's redraw it briefly. We'll revisit this idea. So this is my right angle. This is 30 degrees. This is 60 degrees. This base is 10, right? And this is R, right? But what we know about not just right triangles but similar triangles in general is that you can have two angles that aren't the same size, but if they're the same shape, then everything about them has to be in proportion and in ratios. So if I had a 30, 60, 90 degree triangle whose base was 100 units long instead of 10, then everything will be 10 times bigger. The hypotenuse will be 10 times bigger. The height will be 10 times bigger. And so the same thing should go back the other way, right? If I had a 30, 60 degree, 90 triangle whose base was smaller, say 1, right, 1/10 of it, then the height will be 1/10 and the hypotenuse will be 1/10 of it. And so let's do that. Let's draw a line here and let's say let's go overhead, measure out 1 unit. This is not to scale, of course. And then let's just chop it down here and form a right triangle there. So what we should note though is that this is still 30, right? That angle is exactly the same angle. And because that's 30 and that's a right triangle, this is still 60. So that means this triangle, this 30-60 degree triangle here with base 1 is exactly this a similar triangle to the one that we have drawn here, right? And so this thing has 1/10 the height and it has 1/10 the hypotenuse. Alright? So following that, let's go down and redraw all of this again. And this time instead, what I'm going to do is I'm going to go up here by 1 unit. I'm going to start here. I'm going to walk up until I hit a 1 on the hypotenuse, and then I'm going to drop a perpendicular line down, perpendicular bisector, to make a 30-60 degree triangle here. And so what I know is that this has radius r that I don't know. It has height maybe h that I don't know. And it has base 10. Right? But I know some more about this, right? Than that. I know some things about, I don't know what h and r are, but I do know some dimensions of this triangle here. I know the hypotenuse is length 1. I know that the height is 1/2 and that the base is square root of 3 over 2. Right? And so what I know is that everything, since everything's to scale, and this is 1, and this is r, what I get is that the hypotenuse r is equal to r times the hypotenuse of the unit triangle, which is 1. And that means that the height is r times 1/2, and that the base 10 is r times square root of 3 over 2. Right? And what that is telling me is that the r, in fact, is 20 over the square root of 3. Right? That's the solution to this little bit of algebra here. So if I know what so now I don't know what the radius is. It has to be 20 over root 3 times longer, because this base is 20 over root 3 times longer. So this is 20 over root 3. That takes care of that. And then as far as this goes, h is 20 over root 3 times 1/2, which is 10 over root 3. And that's my height. Right? So that's a concrete expression for how we can find the radius and the height of this triangle based on what we know about right triangles on the unit circle, whose hypotenuse is 1. So let's not tiptoe around the general case. Let's look at what happens when you have a general right triangle with some hypotenuse r, a height h, and a base b. Well, then that again corresponds to some unit version of that right triangle whose hypotenuse is 1. And now we actually do know what we sort of know, we don't know what theta is, but we know how to get the x or the base and the height values. If we knew theta, those are just going to be the cosine values and the sine values of theta, right? If we imagine this being on the unit circle here, and that's the origin, that's the x, that's the y, so that length is cosine and that length is sine. So you again get a series of equations. R is r times 1, big surprise. But now h has to be r times sine theta, and the base is equal r times cosine theta. And so what you can get from that then is that everything still has the same proportions to each other as if they were as in the right triangles with hypotenuse 1. This is cosine sine 1, and this is cosine times r, sine times r, 1 times r. Everything just scales up by r. And so this gives you an alternative way of computing sine and cosine without even having to consider the unit triangle at all. What you can do now is just say, hey, look, if I given a triangle and and its sides and angles, and I want to know the sine or cosine of an angle, what I do know is that if I take the height here and divide it by the radius, so h over r is going to be r sine theta over r, which is sine theta, and b over r is going to be r cosine theta over r, which is just cosine theta. So you get that sine theta is the height over the hypotenuse, and cosine theta is the base over the hypotenuse. Alright? So, of an example of something like that in action, let's take a look at one of the most standard possible right triangles. Let's say it's I don't know what that angle is off the top of my head, but let's look at the 3, 4, 5 right triangle. That's one of the simplest Pythagorean triples, right? And I want to know, alright, if I have a triangle like this, what is cosine of theta and sine of theta? Well, I don't need to. What's going on is that I am scaling down to radius 1, dropping down, and figuring out all of that out. But I don't need to do all that. What I can say is, hey, the sine value is going to be the height divided by the radius. So that's going to be 4 over 5. And the cosine value, that's going to be the base over the radius. So that's 3/5. And then you can double check that if you want. If I did scale everything down, right, this would scale down to 1. So this would necessarily scale down to be 4/5. And this would necessarily scale down to be 3/5. And that's my x, and this is my x, this is my y. So it does exactly what we thought it was going to do. So this is how sines and cosines are computed for right triangles in general, and not just right triangles on the unit circle. But you should keep in your head that it stems back to what we do on the unit circle, and it also underlies why we spend so much time on the unit circle is because problems off the unit circle can be rescaled into problems on the unit circle. Alright, thank you very much. As usual, if you have any questions, please let me know in the discussion board or through email, and I will talk to you in the next video.